My name is Dr. Chris Moore, and I'm a research associate at West Virginia University in the Industrial and Management Systems Engineering Department. And I'm also the project manager of our WVU pollution prevention team. So today, I'll be presenting on the topic of pollution prevention best practices for chemical and manufacturing, processing, and formulation industries. So in this session, the focus will explore many pollution prevention best practices that can be implemented within these industries that can decrease environmental impact and improve or maintain profitability. Since there's a wide variety of processes and methods used in these industries, we'll try to focus on best practices that have the most broad applicability within the sector. So more specifically in this webinar, I'll first provide a brief introduction into pollution prevention as defined by the EPA, the Environmental Protection Agency, and what activities are and aren't considered pollution prevention. Next, I'll discuss EPA's national emphasis areas, which are prioritized industries under EPA's Pollution Prevention Initiative. The main focus of this webinar, however, will be the second national emphasis area, which is chemical manufacturing, processing, and formulation. I'll provide some background into the industry, then cover several pollution prevention best practices that can be implemented by facilities within that industry to minimize their environmental impact and cut pollution at the source. Then after a brief summary, I'll do my best to answer any questions you have. If you have questions along the way, feel free to send them in the chat and I will address them after the webinar. So before diving into the topic of pollution prevention, we first need to understand what pollution is. So according to the Oxford Dictionary, pollution is the introduction into the environment of a substance or thing that has harmful or poisonous effects. So pollution has far-reaching consequences, not only affecting human health, but also disrupting ecosystems and threatening biodiversity. Given these impacts, it's clear that immediate action is needed to reduce pollution and its adverse effects. So pollution prevention, as defined by the US EPA, refers to any practice that reduces, eliminates, or prevents pollution at its source before it's created. This approach differs from pollution control, which typically deals with managing pollution after it has been generated. Instead, P2 focuses on proactive steps to prevent waste and pollution from occurring in the first place. So the hierarchy of pollution management shows a step-by-step approach to managing pollution, starting with the most desirable actions at the top and moving down to least preferred options at the bottom. When possible, the creation of pollution should be prevented in the first place. If the creation of a pollutant can't be completely prevented, the next objective should be to reduce the amount that is created. So when the amount of pollutant can't be feasibly reduced, options to reuse or recycle should be explored. The next step, recover, refers to the process of extracting any useful material or energy from the waste. Then the least preferred option is disposal, where the waste will go to a landfill or otherwise be released out into the environment. So EPA's Pollution Prevention Initiative emphasizes this hierarchy, encouraging a primary goal of preventing and reducing pollution at its source. So as part of the EPA's Pollution Prevention Initiative in 2015, several priority sectors known as national emphasis areas were identified. These 6 sectors were identified as priorities by the EPA Pollution Prevention Program to focus resources and efforts for maximum environmental and economic impact. These sectors offer substantial P2 opportunities and create a focused approach that allows for better resource allocation and the ability to share successful strategies across similar industries. So the original 5 NEAs were the food and beverage manufacturing and processing industry, chemical manufacturing, processing, and formulation, automotive manufacturing and maintenance, aerospace product and parts manufacturing and maintenance, and metal manufacturing and fabrication. A sixth national emphasis area was established several years ago, and instead of focusing on a specific industry sector, the EPA realized the need for assistance with pollution prevention on tribal and native lands within the country. So today's focus will be on the second NEA, chemical manufacturing, processing, and formulation industries. You can find our webinar for the first NEA on our YouTube channel or on our website. And in the coming months, we'll be hosting webinars that cover the remaining 3 industry-related NEAs. So keep an eye out for more information on those. So the food and beverage manufacturing and processing sector includes industries classified in the NAICS industry classification codes, beginning with 325. So as of 2020, there were over 13,500 establishments within the sector, with 3,411 reporting to the toxics release inventory. So this chart shows the volume of waste managed by different approaches from 2011 to 2020 in this industry. So there was a significant increase in the proportion of waste managed through recycling and treatment during this period, as we can see with the size of the green section of the bars increasing. This positive trend indicates growing awareness and adoption of sustainable practices within the industry. The increasing reliance on recycling is a promising development, but these methods not only reduce waste disposal, but also contribute to resource conservation and energy recovery. Despite the progress, though, there's still a substantial volume of waste being disposed of or released, and the amount of waste being disposed has not actually decreased over time. So the recycling has just managed any additional waste that was generated. So there hasn't been much change in any reduction in the amount that's disposed, treated. So this represents an opportunity for further improvement and implementation of pollution prevention practices. So the NEA number 2 industry sector encompasses a wide range of industries that can be kind of divided into 7 categories. So basic chemical manufacturing, resin, synthetic rubber, and artificial and synthetic fiber and filaments, pesticide fertilizer and other agricultural chemicals, pharmaceutical and medicine manufacturing, paint coating and adhesive manufacturing, soap cleaning and toilet preparation manufacturing, and other chemical product and preparation manufacturing. So now that we've briefly discussed the diverse nature of the chemical manufacturing, processing, and formulation sector, let's discuss some best practices for this sector. And these best practices are divided into 4 broad categories. First, we'll discuss some best practices related to spill and toxic release control. Next, we'll discuss proper chemical storage practices. After that, we'll move towards discussing a few P2 practices related to waste management within these industries. And finally, we'll be talking about a P2 practice related to efficient water management. So spill and toxic release control is a significant concern for industries in this sector. Unintended releases and spills of toxic chemicals, depending on the quantity, can have environmental consequences, risk the safety of the employees of the facility and those in nearby communities, and can result in significant costs, including cleanup and other fines or penalties. So let's look at a few P2 best practices related to spill and toxic release control. So they're going to be preparing and maintaining a spill management plan, reducing styrene release in facilities producing styrene-based products, and maintaining optimal reaction conditions to reduce toxic chemical releases. So let's dive deeper into each of these practices, exploring how they can be implemented practically to make chemical manufacturing, processing, and formulation industries safer and more sustainable. First, prepare and maintain a robust, comprehensive spill management plan. Chemical spills are one of the most critical challenges faced by chemical processing and manufacturing industries, and the consequences of these spills can go far beyond the immediate cleanup and can have long-lasting impacts, especially on the environment. So chemical spills can be a concern in many different industries. The chemical manufacturing industries are certain to have large supplies of chemicals, which can make them unique from other industries. So when a chemical spill occurs, it's much more likely to be a large quantity spill, resulting in a much larger impact. So chemical spills can cause environmental damages, including contamination of the soil, water bodies, and the air, which can disrupt ecosystems and can endanger wildlife. Chemical spills also present safety hazards, since the chemicals used are often toxic, flammable, or corrosive in nature and are used in large quantities. These spills can pose significant risks to workers. And if the spill is a large quantity, it can also affect residents in local communities or in other nearby businesses. Next, spills can cause operational disruptions that affect business operations, including delays or halts in production. And furthermore, chemical spills can tarnish a company's reputation, making it harder to maintain customer trust and stakeholder relationships. And additionally, failure to manage spills properly can lead to severe penalties, including fines or even suspension of operations. The Clean Water Act requires many facilities to maintain spill management plans, so failure to have a spill management plan may be a compliance issue in and of itself. And altogether, these issues can lead to significant financial losses, workers' comp costs, penalties and fines, cleanup and mitigation costs, production losses, legal costs, settlements, and other direct and indirect costs are likely to occur from chemical spills. So avoiding chemical spills and reacting quickly and appropriately when they do occur is the best way to minimize these losses. A chemical spill management plan defines these procedures and these requirements. So let's take a look. So a spill management plan serves as a structured and systematic approach to prevention, management, and mitigation of the impacts of spills in industrial settings. Not only does a robust spill management plan help ensure the safety of the employees, but it can also ensure that other damages and impacts are minimized. Responding to a spill promptly and appropriately can help protect employees, the environment, equipment, and other resources. The first step in creating a spill management plan is conducting a risk assessment of the facility. This involves identifying chemicals that are used within the facility, their quantities, their hazards and risks, and potential spill scenarios, and evaluating the risks they pose to people, the environment, and operations. So when possible, steps should be taken to minimize the risk of spills occurring. By understanding the specific hazards and vulnerabilities, we can prioritize preventive measures and be better prepared to respond to incidents. The next step in creating a spill management plan is developing a clear response plan that outlines the step-by-step actions to be taken when a spill occurs, including emergency response, containment of the spill, and mitigation and cleanup. At each step, safety of the employee and others that could be affected by the spill is crucial. Sometimes the most appropriate response will be immediate evacuation of the facility and surrounding areas. So it's essential to define roles and responsibilities for everyone involved to ensure an active and coordinated response, along with effective communication guidelines. Furthermore, there are essential resources that are required for properly managing a spill, including spill kits, containment booms, and any extra protective equipment needed for spill response. These items should always be readily available in sufficient quantities with their locations noted in the spill management plan. Without these resources and prompt access to them, even the most robust spill management plan can fail. And finally, a spill management plan is only effective if it is properly utilized in the time of need. So because of that, every employee that is potentially involved in the spill response, including workers, supervisors, maintenance personnel, etc., must be trained on the spill management plan, along with periodic refresher training to ensure that they are prepared to respond appropriately when a spill occurs. So we've already alluded to many of the benefits, but to summarize, developing and maintaining a robust spill management plan helps ensure that chemical spills are reduced, and when they do occur, that the impacts to the environment and workers' safety are minimized. Since a spill management plan is required by regulation for most, if not all, of the facilities in the chemical manufacturing sector, maintaining a spill management plan will help maintain regulatory compliance, avoiding fines or penalties. Overall, the benefits of a spill management plan result in significant cost savings, helping the bottom line of the business. So the next best practice that we'll discuss surrounds the use of styrene and reducing its release. The styrene, which is also known as ethanol benzene, is a colorless, flammable liquid, and it's commonly used in the chemical manufacturing industry. The styrene is derived from benzene and ethylene via alkylation and dehydrogenation. Styrene has many uses within the chemical manufacturing sector, such as the following. Styrene is the building block of polystyrene plastics. Polystyrene is used to make styrofoam, which is used for insulation foam and disposable food containers and cups. Another use of styrene is in manufacturing synthetic rubber. This type of rubber is used in tires, belts, and the production of footwear. Next, styrene is also used as a solvent in the production of resins and coatings, including paints, adhesives, and sealants. Reinforced plastics, such as those used in automotive and marine industry applications, utilize styrene in their production. And then there are other copolymers like acrylonitrile butadiene styrene, ABS, that are used for making durable goods like appliances and toys, and those also require styrene. So exposure to styrene is harmful for humans and for the ecosystem. Styrene exposure poses significant health risks with a range of acute and long-term effects. Acute exposure to styrene can cause irritation of the eyes and mucous membranes, causing discomfort and potential damage to the respiratory tract. Acute exposure can also lead to systemic issues such as headaches and fatigue, which can affect well-being and reduce productivity. Long-term exposure to styrene can affect the central nervous system, causing dizziness, confusion, and other neurological dysfunctions. Continued exposure can also result in peripheral neuropathy, characterized by nerve damage that impairs mobility and sensation in the extremities. It can cause hearing loss and greatly impacts individuals' quality of life. And furthermore, styrene is classified as a probable human carcinogen, meaning that it's likely to cause cancer with extended exposure. So these health impacts underscore the urgent need for enhanced safety measures in industries handling styrene to protect workers and surrounding communities. So to emphasize the risks of styrene, in May of 2020, there was a tragic styrene leak at a plant in India. This gas leak at it was the LG Polymers plant, resulted in 12 deaths and over 300 hospitalized, and 20 of those that were hospitalized were in severe condition requiring ventilator support to recover. So in addition to the health effects of styrene, releases into the environment can harm aquatic life and contributes to the formation of smog. So what are some steps that can be taken to reduce the risk of styrene exposure? So the best way to avoid the risk of styrene exposure is to not use styrene at all. So as mentioned earlier, styrene has solvent and non-solvent uses. So in processes where styrene is used as a solvent, substituting in a less or non-toxic alternative may be an option, such as acetone or water-based solvents. So on the other hand, when styrene is used more as a building block for plastics or rubbers, switching to, for plastics specifically, switching to polyethylene-based plastics may be a viable option. So getting away from the styrene and using polyethylene instead. So when styrene can't be substituted, processes should be assessed for opportunities to reduce its use. For example, minimizing overspray when spraying styrene-based products and using activated carbon filters to capture the vapor are good options to minimize exposure. Optimizing operating practices is another option. Ensure that styrene storage, transportation, and the use of styrene all follow industry best practices to minimize risk of major accidental releases. So in the case of one Ohio-based plastics product manufacturer, styrene release was reduced from 32,000 pounds to 13,400 pounds over a 10-year period, utilizing these sorts of practices. And that was a 59% reduction in styrene release over that period. They were able to do this by switching from styrene-based cleaners to water-based cleaners, minimizing resin loading and resin mix use, and switching to a closed molding process where the resin isn't exposed to the atmosphere while it's curing. So the next best practice that I'll discuss will be maintaining optimal reaction conditions to reduce toxic chemical releases. Improper chemical reaction conditions can pose significant challenges in the chemical manufacturing and processing industries. So some of the risks of improper chemical reaction conditions are: first, they can lead to the formation of unwanted byproducts. These byproducts can disrupt the desired chemical pathway and reduce the yield of target products. This inefficiency not only wastes raw materials, but it also contributes to reduced reaction efficiency, which ultimately lowers the overall productivity of the process. The generation of byproducts and unoptimized processes results in higher waste management costs. Companies must allocate significant resources towards safely handling, treating, or disposing of chemical waste, leading to higher operating costs. Also, any additional raw materials, energy, and labor that is required to compensate for the inefficiencies will further increase the operating costs. Improper reaction conditions can also compromise the quality of the final product, resulting in a product that may not meet market or regulatory standards, which could damage the company's reputation and customer trust. And finally, improper reaction conditions introduce safety hazards. Deviations in temperature, pressure, or reagent concentrations can result in uncontrolled reactions, potentially leading to fires, explosions, or the release of toxic substances. These risks endanger both workers and the surrounding environment. So there are a few methods that can be used to maintain optimal reaction conditions. Automated monitoring systems are one of the best options. These systems enable real-time tracking of important parameters such as temperature, pressure, and concentration, ensuring that optimal reaction conditions exist. When conditions deviate from expected, the operator will be able to respond immediately. Additionally, collecting and analyzing sample data on the product and analyzing in real time can help ensure that the process is running as expected, ensuring precision and reliability. So by closely monitoring these systems, if things do fall out of line, we can get them back in line quickly and avoid any potential problems. So operator training programs are also going to play a critical role in ensuring that personnel are equipped to manage processes effectively, identify potential issues, and respond appropriately to ensure optimal chemical reaction conditions. And additionally, the condition of the equipment can impact the reaction conditions, so regular assessment and maintenance of process equipment should be implemented. Keeping machinery in top condition prevents malfunctions that can disrupt reactions, create safety risks, or cause chemical reactions to deviate from what is required. So ensuring that chemical reactions are optimized leads to several benefits. Better control over the reaction conditions helps protect the environment by reducing the risk of industrial accidents or disasters and reducing byproducts and waste that may be at risk of ending up in the environment. There are also safety benefits to these as well. Industrial accidents can cause injuries or deaths, and anytime that waste must be handled, it can create additional risks. Optimal reaction conditions also ensure higher product quality, and all these benefits together lead to cost savings and an improved bottom line. So moving on to the next section, we'll discuss a best practice related to chemical handling. And that's going to be implementing proper chemical storage practices. So improper chemical storage practices can cause several issues. Poor storage conditions often lead to chemical deterioration, where chemicals and other stored substances degrade over time, losing their effectiveness and potentially generating hazardous byproducts. This often happens when an accurate chemical inventory is not maintained and chemicals are quote unquote lost. If these degraded chemicals are eventually used, it can affect the quality of the final product. Another critical issue is increased risk of leaks and spills. Improperly sealed or stored chemicals can escape their containers, leading to environmental contamination, workplace hazards, and cleanup challenges. These incidents also contribute to increased chemical waste, as spilled or degraded chemicals can no longer be utilized, requiring additional resources for disposal. The combination of these factors creates significant safety hazards. Leaks, emissions, and deteriorated chemicals can increase the risk of fires, explosions, and other toxic exposures, posing a serious threat to both workers and, in large enough quantities, to surrounding communities. Additionally, improper storage heightens the risk of toxic emissions, which can harm workers' health, pollute the environment, and result in legal and reputational damage for companies. So altogether, these problems lead to various financial costs, leading to unnecessary financial losses. So the following are steps that should be taken when storing and organizing chemicals. So the first step above all of this is going to be creating a chemical inventory. So the amount and location of each chemical in the facility should be recorded and maintained, and safety data sheets for each of these chemicals should be compiled and readily available in the facility. During this time, the following practices should also be implemented. So the first is going to be classification and segregation. So chemicals should be grouped and stored based on their compatibility to prevent dangerous reactions, such as mixing acids with bases or oxidizers with flammable substances. This practice minimizes risks and ensures safer handling. Next is going to be labeling and containment. Proper labeling ensures that every container is clearly identified with its contents, hazards, and handling instructions. Additionally, secure containment prevents leaks, spills, and exposure to harmful chemicals, safeguarding workers and the environment. So environmental factors such as temperature, humidity, and ventilation must also be carefully monitored and regulated to prevent chemical deterioration or unintended reactions. Chemicals need to be protected from external harm, such as physical damage, fire hazards, or other contamination. So proper shelving, spill containment systems, and fire suppression mechanisms are all essential measures to ensuring safety. And finally, routine inspections are crucial. Regular checks can identify and address potential issues like damaged containers, labeling errors, or deteriorating conditions before they escalate into significant problems. But again, all of this starts with maintaining a chemical inventory in just knowing where all of your chemicals are. The proper chemical storage practices offer significant benefits to the chemical manufacturing industries. So first is going to be environmental protection. These practices prevent spills, leaks, and toxic emissions, reducing the risk of contamination to soil, air, and water. Proper storage ensures chemicals remain stable and usable for longer periods of time, leading to reduced chemical waste and more efficient utilization of resources. Industries also benefit from regulatory compliance, as adhering to storage standards helps meet legal requirements, avoiding unnecessary fines or penalties. Also, minimizing loss from wasted chemicals, unnecessary repurchases, accident-related downtime, and other cleanup due to improper storage leads to cost savings. And finally, these practices significantly enhance safety by reducing the risk of fires, toxic exposures, and hazardous reactions, creating a safer environment for workers and surrounding communities. So next, let's talk a little bit about waste management. So waste management is crucial in these industries, as the waste is often more toxic than in other industries. Since different chemical wastes have different properties, preparing and implementing specific waste disposal plans is a step that can be taken to reduce risks. Improper waste management can cause a multitude of problems. For example, it creates environmental hazards since it increases the chances of toxic chemicals being discarded improperly. Improper waste management, specifically mixing incompatible chemical wastes, can lead to unintended reactions such as the release of toxic fumes, corrosive substances, or hazardous byproducts. This can cause significant harm to the environment by contaminating water, soil, and air, posing long-term ecological consequences. It also risks the safety of employees and nearby residents and businesses. Moreover, mixing chemical waste complicates the separation and treatment processes, making management and disposal more resource-intensive and time-consuming. Specialized treatment would likely be needed, which increases waste disposal fees and leading to lower operational efficiency. There are also potential fines for violating waste management regulations. So furthermore, incompatible chemical mixtures can release harmful gases or vapors, endangering not only workers, but also nearby communities and ecosystems when quantities are large. These emissions can also result in regulatory violations and reputational damage. So some chemicals as waste can be mixed together if they're compatible, but if there's any uncertainty, chemical waste should be isolated individually. Some of the guidelines for chemical compatibility when it comes to waste disposal are as follows. So first, waste from strong acids and strong bases should be stored separately in corrosion-resistant containers with the contents labeled clearly. If waste from acid and bases are mixed in an uncontrolled manner, it can result in unpredictable chemical reactions and generation of extreme heat and dangerous fumes. For disposal, acids and bases can often be neutralized in a controlled manner to create pH-neutral solutions that are easier to dispose of. So, for example, sulfuric acid waste from fertilizer production and sodium hydroxide waste from soap manufacturing can both undergo a neutralization process. However, care must be taken when selecting the neutralization agent, and the process should be monitored and controlled carefully to maintain safety. Organic solvent waste should be isolated, as it requires specialized disposal. Since these solvents are often toxic and volatile, their disposal involves incineration at high temperatures and facilities with pollution controls. Wastes from heavy metals like lead and mercury should be stored separately, also requiring specialized disposal. Heavy metals are highly toxic and persistent, which means they remain in the environment for long periods without breaking down and that can lead them to transferring through the food chain and bioaccumulate. These wastes must be treated through precipitation and solidification, turning them into stable forms before they can be landfilled or recycled. For example, mercury waste from chloralkali plants and lead residues from battery recycling require careful containment in labeled, leak-proof containers to prevent leaks or exposure. Waste from reactive chemicals, which are substances that can react violently with the air, water, and other chemicals, have to be handled carefully. These violent reactions are associated with extreme releases of energy, including toxic fumes, heat, fire, or explosions. These wastes must be neutralized through controlled deactivation or dilution, making them inert before disposal. As an example, sodium metal waste from petrochemical refining and peroxide-containing waste from polymerization processes must be stored separately from incompatible substances and heat sources to avoid potential risks. Improper disposal of pharmaceutical waste, including expired drugs or solvent residues, can lead to contamination of water supplies and ecosystems. Pharmaceutical waste management involves segregating active and non-active pharmaceuticals, followed by incineration or chemical treatment. Radioactive waste, which is often generated in the chemical processing industry through the use of catalysts or tracer studies, requires segregation based on its half-life, along with shielding during storage to prevent radiation exposure. For example, uranium or thorium used in catalysts, as well as low-level radioactive isotopes, must be logged in detailed records, handled under strict protocols before being sent to specialized facilities for disposal. Biological waste presents another challenge, especially in bio-based production industries. This waste includes materials contaminated with infectious agents, such as enzyme residues from pharmaceutical fermentation or from microbial byproducts. The disposal process involves autoclaving or incineration, which sterilizes the material before final disposal. So to ensure safety, biological waste should be collected in biohazard marked containers and handled with appropriate personal protective equipment. And finally, cyanides, which are extremely toxic and reactive, their disposal plan focuses on oxidation, which converts them into less harmful cyanates, followed by neutralization. For example, cyanide-containing effluents from synthetic fiber production must be handled with great care, stored in secure containers, and kept away from acids to avoid releasing hydrogen cyanide gas, which is highly dangerous. So as you can imagine, mixing these different types of waste together will make avoiding mixing them together will make safe, proper disposal easier and less expensive compared to if you have a mixture of all these things. Disposal is extremely challenging. It's expensive and it can be dangerous. So appropriate chemical-specific waste management will have several benefits. First and foremost, these plans ensure environmental protection by preventing harmful waste from contaminating soil, air, and water, thus preserving ecosystems. Secondly, they facilitate resource recovery by enabling the segregation and recycling of reusable materials, reducing overall waste and promoting sustainability. Furthermore, these practices also help industries achieve regulatory compliance, avoiding penalties while maintaining a positive reputation for adhering to environmental laws. Additionally, appropriate chemical-specific waste management offers cost savings by minimizing waste disposal fees and reducing the need for remediation after accidents or spills. And finally, proper waste disposal plans significantly enhance workplace safety by mitigating risks associated with hazardous chemical reactions, reducing the likelihood of fires, toxic emissions, and worker exposure to harmful substances. So in the previous slides, we briefly discussed neutralization of waste acids, but there is another potential option there, and that's the recovery of acids using a diffusion dialysis recovery system. So first, let's talk about the consequences of improper disposal of acid waste. So acid waste poses environmental hazards, as improper disposal can lead to soil degradation, water contamination, and harm to aquatic ecosystems. Such pollution can have long-term ecological consequences and damage biodiversity. In the workplace, acid waste introduces significant hazards, as exposures to acidic substances can cause burns, corrosion of equipment, and dangerous reactions that increase the risk of fires or toxic emissions, jeopardizing worker safety. Also, failing to manage acid waste properly can result in regulatory compliance issues. Strict environmental laws govern acid waste disposal, and violations can lead to heavy fines, operational shutdowns, and reputational damage. And waste of many acids can be recovered for reuse, but without proper systems in place, these valuable resources are lost. So the solution here, as I said, is implementing a diffusion dialysis acid recovery system. And this is one of the most effective methods of recovering acids for reuse. So a diffusion dialysis acid recovery system is a membrane-based separation technology. And in these systems, acid waste is passed to a specialized diffusion dialysis unit containing semi-permeable membranes. These membranes allow acids to selectively diffuse through, separating the usable acid from impurities in the waste. The recovered acid that's diffused through the membrane is collected, ready for reuse in the production process, while the remaining impurities and waste can be safely disposed of. So the system as a whole kind of works as follows. The used acid is metered through the system and is in contact with one side of the membrane. And that's an anionic exchange membrane. So water, on the other hand, is metered in a countercurrent fashion on the recovery side of the membrane, which causes the majority of the acid to migrate through the membrane, rejecting contaminants such as heavy metals along the way. Then the purified acid and water is directed back to the process tank, while the contaminated spent acid stream continues to the metal recovery waste treatment for further processing. And fresh acid in proportion to the unrecovered amount is added to the bath to maintain the concentration within the correct operating parameters. So in one case study, a stainless steel fittings manufacturer was able to recover 80% of the nitric acid they used in the process using this technology. So the use of diffusion dialysis acid recovery systems helps to recover acids and reduce hazardous waste resulting from acid contaminations. This leads to multiple benefits, including protection of the environment from the acid waste, resource recovery, maintaining compliance with regulations, and altogether financial savings. So as I was mentioning, in this one case, there's an Illinois manufacturer of stainless steel fittings and flanges. They operated a 1,500 gallon pickling bath composed of nitric acid and ammonium bifluoride. And they were changing this bath every 6 to 8 weeks, or about 7 times per year. And as a result of this, they were incurring annual costs of $18,000 for disposal and $13,000 for fresh chemicals. So some engineers from the Illinois Sustainable Technology Center assisted them with implementing a diffusion dialysis acid recovery system, which allowed them to recover 86% of the nitric acid and 30% of the ammonium bifluoride. So this reduced their need to recharge the bath from 7 times per year to 2 times per year. So that proved to be a cost-effective and sustainable solution that saved them upwards of $10,000 a year. So there were reduced disposal costs, reduced chemical costs, reduced pickling time, and decreased rework with those modifications. And finally, the last category will be water management. So fresh water is one of the most valuable resources. Every action to save water is a step towards building a sustainable future. So in this final section, we'll be discussing pollution prevention best practice related to water management in one chemical manufacturing industry. And specifically, that's going to be treating and reusing effluent water in bioethanol production. So bioethanol is a promising source of renewable energy, but the process, production of bioethanol requires significant amounts of water, requiring multiple gallons of water to be used for each gallon of bioethanol produced. So there are two primary types of bioethanol production, and each of these do require a large amount of water. So that's the corn grain ethanol and cellulosic ethanol. So corn grain ethanol is produced in a process of grinding, liquefying, fermenting, and distilling corn. Most bioethanol is produced using this method due to lower capital costs. The water is required in almost every step of this process, resulting in a use of 3 to 4 gallons of water to produce 1 gallon of bioethanol. Cellulosic ethanol, on the other hand, is produced in a biochemical process where the cellulose in biomass, such as grass and wood chips, is hydrolyzed into sugars, then fermented into ethanol. So during this process, pretreatment, enzyme hydrolysis, and fermentation all require a significant amount of water, with 6 to 10 gallons of water required to produce each gallon of ethanol. So while bioethanol is much more environmentally friendly in use than petroleum-based fuels, we have to consider the environmental impact of the water usage as well. So high water consumption places tremendous strain on local water resources, especially in regions where water availability is already limited. And furthermore, as bioethanol production continues to expand to meet renewable energy goals, concerns about the sustainability of this water usage continue to grow. So ensuring efficient water management is critical not only for the industry's growth, but also for protecting our natural resources. So the solution here, or one possible solution here, is to utilize effluent wastewater instead of using fresh potable water for the process. So by sending effluent water through a multi-stage filtration process, followed by a disinfection process, the water can be reused in the production of bioethanol. So during the filtration stage, large solids are first removed. Afterward, the wastewater is allowed to settle and physically separate to remove the remainder of the solids. And next, the water is filtered through a membrane, then treated biologically. Then during the disinfection stage, the filtered water is treated with UV, followed by a chemical treatment. And at that point, it can be reused in the bioethanol production process. So the use of treated effluent water in bioethanol production offers several benefits that can significantly enhance the industry's sustainability. So first and foremost, it conserves fresh potable water. So by reusing treated effluent water, the industry can reduce its reliance on freshwater resources, minimizing the strain on local ecosystems and preserving natural water supplies. This approach helps mitigate the environmental footprint of bioethanol production. Next, treated effluent water, which might otherwise be wasted, is turned into a valuable input for the production process. This not only maximizes the utility of existing resources, but also contributes to a circular economy within the industry. Regulatory compliance is another key benefit. Many regions are implementing stricter water usage and waste disposal regulations. By using treated effluent water, bioethanol plants can meet these requirements more effectively, reducing the risk of penalties or operational shutdowns. And finally, associated cost savings. So by reducing the dependency on expensive fresh water, these producers can achieve significant economic benefits over time. So over the past 50 minutes, I covered quite a few pollution prevention best practices, most of which have widespread applicability in the chemical manufacturing sector. I hope that you're able to take something away from this that you can utilize moving forward. So for more information on any of these best practices, including technical assistance, please reach out to myself or Dr. Ashish Nambarke. Also, please feel free to reach out to us for any other information or assistance related to pollution prevention as it applies to the NEAs or to other industries, and we'll do our best to help you out. All right. I'd like to thank you all for your time today. I hope you enjoyed the presentation, and I also hope you look forward to seeing you at our future webinars on the remaining 3 industrial NEAs from the EPA. All right. Thank you all for your time and have a great day.